Continue worksheet 60 day. After we find out the equation for moment curve, we can apply the integral beam equation, which is the first is the slope function y prime equal to 1 over ei mx dx, and take another integral, we can get the elastic curve function. So let's go back here. The next is will be slope curve. What does that mean? We want to find out the angle theta for the deflection at any given point, and that with the y prime x equal to 1 over ei integral of mx dx, plug in mx equal to cx over L, so we can have that here cx over L dx, and CL is constant, so we can have that is with that integral it equal to 1 over ei cx squared over 2L plus C3, and C3 is the boundary, get it from the boundary condition. Let's go back here to see the end condition for the pins. As you can see, the theta similar at roller at end or pin at ends, the theta, the slope at A are non-zero, but in this case we don't know yet. So as you can see, yes, it there is boundary condition, but we cannot find out at this point. So it's equivalent to, you can say that no meaningful boundary condition, no, and we don't know theta at A yet. So we can say no boundary condition for now. Hopefully the next one may have it to show, otherwise it will be tricky. No boundary condition for slope curve in this case. So save the best for last. We can continue to find out the elastic curve, which is y-axis, elastic curve y-axis. So y-axis equal to the second, the double integral of mx dx from the integral beam equation that you can see there, or it equal to the first integral of yx over ei of the y apostrophe or y prime dx. It equal to plug in cx squared over 2L plus C3 dx, and that one yx with that integral we have it 1 over ei cx squared over 2L, it will be cx cubed over 3 times 2, so it will be 6L plus, here is C3 not C2, and we have it C3 here, so C3 becomes C3x, and then plus C4, another constant that we have it for the integral of this case. So boundary condition, and I don't have to go back to the end condition in the note again, but as you can see for this one, no deflection at A and no deflection of B for the pin at N or the roller at N, which is y at A equals 0 and y at B equals 0. So what do that mean here for the boundary condition? As you can see, we have what? We have I y at A equals 0. So from that, when we plug in x equals 0 in y-axis, so I have that equal to C4 equal to 0. And then similarly, y at L, which is at B, no deflection at the roller at B, so it's 0, and plug in the 1, we have that it will be C L cube over 6L plus C3L, and that equal to 0. We can find out C3 equal to negative CL over 6. So from that, we can plug into that equation. We can find out Ix equal to the y-axis, which is the elastic curve function, equal to 1 over EI, and C4 equals 0, C3 equal to negative CL over 6. So we have CX cubed over 6L minus CL over 6 and C3X. So we have a CX in there. So that is the first answer for number 8. And you can see here, part A. And the question also asks, what is the determine the magnitude and location of the maximum deflection? How can we do that for the maximum deflection? And you can see the maximum deflection is the when get the maximum deflection for the curve when the slope equal to 0, or the first derivative of elastic curve function equal to 0. So to find out the maximum, that is the question B, what is y max, and the location of that maximum deflection. How can we find out? And you can see here, y max when the first derivative equals 0 or slope equal to 0. So when slope equals 0, we have the slope equation on the left here, y prime. So plug in that one. We have y prime x equal to 1 over EI CX squared over 2L plus C3 now. We already find out negative CL over 6. So plug in here CL over 6. And that have to be equal to 0. And from that, we can find out that x squared equal to L squared over 3. Or we can have x square root equal to L over square root of 3. So that is the location make y max equals 0. And then we just find out what is the maximum deflection by plug that number into the y-axis equation in here. So we can have y at L square root of 3 equal to 1 over EI 1 over EI, plug in the equation we have down here, down there. So you have C over 6L x cubed, so it will L over square root of 3 cubed minus CL over 6 x times L over square root of 3 total. And from that we can simplify. We have y max equal to negative CL square over EI and 9 square root of 3. So that is the y max we need to find out. So up here I can rewrite that equation to make it a better notation for this equation here. Y x in this case equal to y at L square root of 3 equal to 1 over EI C over 2 sig L x equal to L over square root of 3 minus CL over 6, and then XL over square root of 3. And with that, we get the Y max at its habit in here. So that is the answer and complete this problem for worksheet 69.